Marinus insights to Titan's hydrology, since the additional material I put in was some recent work my group's been doing on understanding Titan's lakes and seas and how they fit into Titan, which is the largest moon of Saturn's overall hydrologic system. And there's some really exciting results that are just now coming out of the Cassini mission. Despite the fact that Cassini burned up in Saturn's atmosphere in 2017, there's still a lot of science to be garnered out of that data set. And I'll be talking about how we're massaging the data to pull that out and some of the new discoveries that we found. I guess we don't have a slide changer. Oh, no, we do. Okay, so, but I do want to produce some background information. I think the issue is the delay that I was worried about is happening. And that is that the story of our exploration of the ocean worlds of the outer solar system really parallels the story of the exploration of our own oceans. And for the majority of the history of human exploration, the deep oceans were a place of fanciful imagination where monsters would be eating your ships, and we didn't know what was underneath the ocean. And that's very similar to the pre-Voyager days of planetary exploration. We didn't know what was out there, and if you look at some of the predictions and some of the fiction that talked about, say, sirens on Titan, there's a lot of variety. And that all changed for the oceans with the HMS Challenger in the late 1800s, which went around the coast of Australia and found roughly 2,000 never-before-seen species, and is consistently considered the birth of modern oceanography. That to me is the parallel of the Voyager missions, discovering for the first time the variety of landscapes and materials and processes and moons that we see out past the asteroid belt. And then but despite that, even after the HMS Challenger, the deepest, darkest parts of the ocean where the sun didn't shine were considered to be barren wastelands devoid of life. That changed in 1977 when a group from the Woods Hole Oceanographic Institute were going to study what they thought would be a hydrothermal or hot vent at the base of the ocean off the coast of Ecuador associated with plate tectonics. And the Alvin submersible here did find a vent, but also found a rich biosphere that was being supported from the vent. And if you ever look at the history of that exploration, it's really kind of interesting. So Jack Corliss, who was the scientist who was driving Alvin at the time, has a recording of his discussion with his graduate student on the boat, asking, there's supposed to be a barren desert down here, right? No life. And the student says, yes. And he's like, well, why am I following clamshells? Why do I see things down here? And it was something they completely didn't expect. So much so that there was only one reporter, a guy named Perlman from the San Francisco Chronicle, who got the scoop on the discovery of hydrothermal vents on that boat. 2 years later, another expedition was sponsored by the National Science Foundation, and they went out and brought a whole host of biologists as well as National Geographic. And my favorite National Geographic documentary is actually Dive to the Edge of Creation, which chronicles that 1979 revisit to the hydrothermal vents off Ecuador. Where this parallels outer planet exploration is that within 6 weeks of that second expedition, we received our first images in 1979 of Jupiter's moon Europa from the Voyager spacecraft. And these images came back showing a body that looked nothing like Earth's moon. It's not a battered surface of craters. Instead, you have these crisscrossing lineae that go across the surface that, if they were able to move independent of the interior, could do so if there was an internal ocean. And Bob Parpalardo, who is the current project scientist of NASA's new mission to Europa, was one of the first to make that suggestion in a paper. But the actual discovery of an ocean at Europa was not made until 1999-2000 timeframe, when the Galileo mission went to visit Jupiter, which was a flagship mission by NASA that orbited Jupiter studying its moons. And this is a picture from Galileo. And I wanted to include this picture here because of the discovery of that ocean is attributed to the magnetometer instrument on Galileo, and it was led by Margie Kibbelson, a picture of whom is right here. And that discovery of that ocean was based on the fact that as the spacecraft got near Europa, Europa is traveling through Jupiter's very strong electromagnetic field, and that magnetic field and the orbit of Europa are tilted with respect to each other. So there's a gradient in the field as Europa orbits through it, and that means you have a time-varying magnetic field, which creates an induced field, the same way a metal detector works, and that's what the spacecraft determined when you got near closest approach of Europa. The magnitude of the magnetic field went up, Here's the magnitude here. And the only way that you could have got this increase is that you had an extreme conductor present. And the only conductor that was plausible, that was large enough, is a liquid water ocean, a salty liquid water ocean. And so this is credited with the discovery of the first ocean world. And the reason I wanted to bring this up too is that this week is also the Project Science Group meeting, or the team meeting for the Europa Clipper spacecraft in Pasadena, California. So I thank you very much for the invitation to come here, because it means I didn't have to travel all the way to California. I was able to say I already had a commitment. I love it. I'm just 3 hours from home. I'll be home on Tuesday as opposed to being gone all week. Thank you. But at a previous PSG, we're a bunch of we have a high prevalence of science fiction fans in the NASA mission community, and we give out a monolith award at every one of these PSGs to somebody who did something amazing in Europa science. And for those of you who saw Space 2001, you know why we use a monolith award. But Margie got the monolith award at a meeting at University of Michigan now, like 6 years ago. It's been a while, but she gave one of the most moving speeches that I think I've ever seen at an award ceremony, because she showed a series of slides of what it was like to be a female physicist growing up in the 50s, 60s, 70s. Pictures of her in her graduate class off on the side by herself. And then maybe she's in the group a little bit later when she's an assistant professor, until more and more female physicists are in the room with her. And then she looks up after giving this wonderful speech and sees that there's more females than males in the room for the award ceremony. And so there's this great picture of her that was then put on social media of all the female co-Is from Europa Clipper. And it was just a very moving period. So I thought it would be fun to share that because of the connection to the PSG today. Moving on though, Europa was the first, but now we know there are more than a dozen ocean worlds in the outer solar system that are in reach, that are defined as moons of the outer solar system with icy crusts beneath which there are liquid water oceans, some of which have high pressure ice layers at their base, some of which are small enough, like Europa and Enceladus, to have directly rocky interactions. But 4, if you include Mars, we can debate whether you want to do that, are special in terms of the search for life in the solar system. And they're the ones that I'll focus on for today, with a heavy interest in Saturn and Titan. So Ceres and Mars are relic ocean worlds. They're places that we think had oceans in the past on their surfaces, whereas all these other ones have oceans beneath their icy crusts, or at least propose to potentially have oceans beneath their icy crusts. And so this kind of dates me with one of my favorite movies. I need to find, my students keep telling me I need to find a new analogy here, but here's the usual suspects for life in the solar system. You have Mars, Europa, Enceladus, and Titan, and each one has its own unique attribute and goals for future exploration. For Mars, well, Mars is all about ancient life. Mars was habitable 3.5, 4 billion years ago. And the question now is, was it inhabited then? Some people think there could be minor environments on Mars that could be habitable today. But the real question for Mars is, was it inhabited in the past when liquid water was prevalent on the surface? And to understand that, we're really doing what is important. We're bringing back a sample, and that's Mars sample return. That's the next step on Mars. On Europa, I'll argue it's potentially, when you list all the qualities that moon has, people would argue it's the best place for conventional life as you know it to exist, although it's still a lot we don't know. And what we first have to understand is what is the ice-ocean exchange processes? What kind of materials are we getting down into the ocean at Europa, and what are the properties of that ocean? Enceladus is spewing material into space, and it's the easiest to explore and most studied ocean. And we're directly at the point now for Enceladus. The next mission going to Enceladus will be actually directly looking for signs of life. And then Titan is the largest moon of Saturn. And on Titan, it has something these other ones don't in terms of plentiful organics on the surface that I'll talk to you about in a little bit, that have relevance not only for life today on Titan, which is a world of 2 oceans, a liquid water ocean underneath its icy crust and hydrocarbon oceans on its surface, but also relevant to life on Earth, since some of the atmospheric chemistry going on Titan today is very similar to the atmospheric chemistry that went on early Earth during the emergence of life. But I'll quickly just mention Mars. So this top mosaic is one I stole from the team. We made it just 2 days ago. You'll see it in the news. It'll be released soon. This is called the Sample Depot. So Perseverance rover on Mars 2020 just finished collecting its first suite of samples, and we just dropped them off on the surface for later pickup. And they're inside this mosaic. There's little white things. They're hard to see. So I have a zoom up here on the bottom. This is taken about 30 days ago at the start of that Sample Depot activity. showing this sample tube, number 34, dropped on the surface underneath the rover. The rover kind of drops the samples off like droppings and keeps driving away, and just leaves them on the surface for later pickup. It's also, I love this picture too, because you see our little rock buddy that's been with the mission since the first week, just kind of hanging out in the bottom of the wheel, rattling around as we drove. And there's some other rocks that get stuck in the wheel. This one's been here about a month and will probably fall off, and another one will get picked up. Yeah. Sure you can. Is there a chance that there was a big dust storm that those samples would get covered up? I do not think that you can cover them up in the time scale of when we're going to pick them up. And that math has been done. But I will also point out that these are the backups. Okay. This is the backup. The main goal is we have another sample. Every one of these samples is doubled up. And the other cache is going to be placed at a location deemed to be the landing event for the next mission, which I'll show you in a second. And a robotic arm goes out and grabs them. If something fails with that robotic arm, there'll be little helicopters that will fly to the sample depot and pick up these vials. But you're not going to deposit enough to bury those in the 10 years it takes to send the mission out there. Now, with NASA's budgetary problems, who knows? Maybe they'll have to sit there for a few hundred years and it'll become an issue. This is what a sample looks like, and it's not lost on the team that this has a similarity to something else in the sci-fi world. So you can see there's a lot of lightsaber jokes that running around the team right now, but that's what a sample tube looks like. But let's move off Mars and continue to the outer solar system. Although I did want to mention this, I will say this photo makes me sad and happy. It makes me happy because of how far we've gone with Mars exploration. This is a plot of just the US missions to Mars and the progression leading up to Mars sample return, and ultimately the launch in 2026 of the Mars Ascent Vehicle, which is the thing that's going to bring those samples from the surface of Mars back into orbit. Then another mission that's launched by ESA called the Earth Return Orbiter will pick them up in Mars orbit and ultimately bring them back to Earth. So it's a 3-mission survey that will be dominating our budget for years to come. But sample science is the gift that keeps on giving. And so once we get these samples back to Earth, every instrument on Earth is able to investigate them. And, you know, one way I like to think about sample science is that the best questions we're answering about the moon are happening today using samples collected in the 1970s. And the science questions we're answering are questions we didn't know to ask then. And they're being asked by and the experiments conducted by scientists that weren't alive when those samples were collected. So sample science really is that gift that keeps on giving. But if we had this many missions in the outer solar system, I would be so happy. And that's why I'm sad. Because if I made this plot for the outer solar system, there'd be 3 missions. But Europa, back to just talk about that, has a substantial amount of tidal heating as it goes through its orbit around Jupiter. But again, I don't want to focus on things you heard from Amanda. And that allows it to maintain a liquid water ocean that's got twice as much volume as all Earth's soap oceans combined, amongst a thin ice shell that's 5 to 20 kilometers thick. And one of the goals of the next mission to Europa, called Europa Clipper, is to try to estimate how thick that ice shell is and what the timescales are for moving material from the surface into that liquid water ocean. The other reason I bring it up is to keep our story going of those parallels. Within just a few months again of that discovery of defining the ocean at Europa through Margie Kibbleson's magnetometer work with Kishan Khurana, her then postdoc, now a faculty member at UCLA, another team of oceanographers, this time from the University of Washington, discovered a different set of hydrothermal vents in the Atlantic Ocean at a place called Lost City, which are carbonate chimneys that have at least 30,000 years of growth on them and support life up to small scales, not by having to have any interaction with hot magma or magma wells underneath. These white smoke, as they're called, are driven by serpentinization reaction, where fresh mantle rock is just interacting with seawater in a reaction that produces energy and heat. And so now this is even more relevant to the outer solar system because we don't have to have hot magma. We just need to have fresh rock interacting with salty ocean water, which we have. And there's James Cameron did a documentary of this Lost City science team called Aliens of the Deep. It's not as good as Dive to the Depth of Creation, in my opinion, but it's a close second. All right, so Europa, best place for conventional life, as I already mentioned. You have an ocean twice the volume as Earth. You have direct interaction with rock. You have possible mechanisms to basically maintain energy through redox reactions by radiolysis of surface ice that makes its way to the ocean. But there's a lot that's not known. We don't know how many organics are present. We don't know what the pH of the water is. And To try to get at some of that, well, the next mission NASA has decided to make its flagship is Europa Clipper. It's launching next year. It's an orbiter meant to understand the properties of Europa's surface, the composition of various things on the surface, and the mechanisms that might be potentially present to cycle that ice back into the ocean. Just to give you a sense of how much we're going to learn, this is an image of showing the pixel scale we have of Europa today, taken by that Galileo mission in 1995 to early 2000s. The yellow here, which is most of the surface, is at around 1 kilometer per pixel. That's what we have is kilometer per pixel scales. Whereas Europa Clipper has the potential, not the data volume, but the potential. So that same yellow area now is sitting at 3 meters per pixel, factor of 1,000 increase. Okay, that's substantial. Okay, and there's of course many instruments that I won't get into, so we can talk more about Titan. But in order to look for life at Europa, I do show a picture here of a mission that has a lot of planning gone into it, but it's not currently on NASA's books, nor was it recommended by the Decadal Survey. This is called Europa Lander, and it's the mission that would go buzzsaw into the surface of Europa because this ice was originally part of the ocean in the past and look for evidence of life in the ice on Europa's surface. And this is a mission that'll be reevaluated again in roughly 10 years by the next Decadal Survey. However, going to Saturn's moon Enceladus, we can directly look for life today, and I believe your professor is hoping to do just that. Your Enceladus is a tiny moon of Saturn that would fit between San Francisco and Los Angeles. And it was always known to be interesting because Voyager showed it to be the brightest reflective object in the solar system in terms of a moon, and we didn't know why. When Cassini got there, again, I have this whole story that we're not going to tell because we want to get the Titan. But at the base of Enceladus in the South Pole, there's these fractures. There's several dozen fractures that are just spewing material into space. These were discovered in 2005. It's kind of a funny story. By the magnetometer, should get the credit for this discovery again. When Cassini first went by this moon, the camera system caught a picture of these guys in an off-axis angle, and the camera PI, Carolyn Porco, got all upset because she thought there was a stray light issue in her camera and started getting her team to look at calibration of the camera and fix it. Why are we doing this? This is bad. And the magnetometer team said, hey, why does that moon look more like a comet with a tail than a moon? Go back and look at it again. When they went back and looked again, the camera system took another picture and saw these beautiful fractures that are spewing material directly into space. We didn't know it was sublimation or water, but spewing material into space. And so I guess emphasize, because I don't think they get the credit they deserve. The magnetometer team gets the credit, in my opinion, for discovering the fractures and ultimately their importance, but the camera then characterized them. Again, and then Cassini was orbiting Saturn, doing exploration of several of its moons. So it takes some years. In 2008, they went through these fracture patterns. They went through the deposits from these fracture patterns and found organics, which made them really interesting. And in 2010, they then found salts in there. And in order to get the concentration of salts that they found, they said there had to be a salty liquid water source. In fact, the way to think about it is, I don't know if any of you guys has done this dumb thing that I've done a few times, I don't know why, which is taking a small boat out in the Northeast, say Long Island's waters or off the coast of Boston in the middle of the winter. Has anyone done that? Been on a small boat in the middle of the winter driving through the Northeast? There's always one person. I guess I'm the only fool. What happened? What was hurting you? What happened? So what happened to me, at least, is that waves that crash over the bow of the boat instantly freeze, and you get pelted by what's called sea spray, which are these little hail balls that smack in your face. And they're an exact analogy for what's coming out of these plumes. And that's exactly how we know that they're salty. Later on, in 2015, they discovered small-scale silica grains inside the plumes that can only exist if rock had dissolved into the water, which only happens at near boiling temperatures. And then in 2017, there was a big discovery of hydrogen in the plumes, which said that you have an energy source. So at Enceladus, again, I don't want to spend too much time on it, but it's the most known about ocean. We know there's a liquid water ocean from work from gravity and also some topography studies. We know it's global, we know it's salty, and we know that there's hydrothermal systems at its base. And that's pretty exciting. Yeah. Because that's the only way to get nano-sized silica grains out. This is a paper by HSU Hugh in 2015, so you can look it up. It is to dissolve. So ultimately the rock, the silica, was dissolved in the water, and then as the water was cooling down as it froze, it precipitated out those nanometer-sized grains. It's the only way how to do it. And the only way for the water to originally get the silicate in it is for it to be under certain conditions that are near boiling. And there are people like Kate and Chris that can augment that if you'd like. Okay, but here's one of my favorite pictures of planetary science I just had to show. This is an image of Saturn occulting the sun, taken by the Cassini spacecraft just outside the plane, just inclined from the plane of the satellites. And this dusty ring here is the E-ring of Saturn. And we knew Enceladus was in a ring of Saturn. What we know now is that Enceladus is making that ring from its plumes. And the reason it's so bright is it's literally spray painting itself, which is kind of cool. Earth and the moon, if you really zoom in, are also in this photo. And we could go on and on about the physics of this photo and how you can see the rings behind Saturn because of refracted light. There's so much fun science and physics here. Feel free to ask me about it afterwards. And you might actually see this scene in some upcoming sci-fi movies because we've tried to sell this to various directors about you have to show a movie like this. All right, but Enceladus, easier to explore, most known about ocean, saltwater ocean with established hydrothermal activity. You're reliably expressing that ocean into space through a big plume. We've demonstrated with a spacecraft already you can fly through and test it. And by today's standard, it's the most habitable place known off Earth. And the next question is whether there is life at the base of Enceladus' ocean in these hydrothermal systems. And the recent Planetary Science Decadal Survey, which is NASA's way of getting community input on what should be the priorities for the next decade, set a second priority flagship. The first one is to go to Uranus, is actually to go back to Enceladus with flagship multi-billion-dollar resources to ultimately land on the surface and just let yourself get sample rain down on top of you. And then you can really study in detail what is in there. Other missions, though, are trying to do it before this orbital lander through competition for lower class programs at NASA, the more billion-dollar class. There's a collection of proposals here. I didn't put all of them on, but they're all proposing now a couple of these to the upcoming competition to study Enceladus. And so there is quite a lot of interest to go back to Enceladus. I will say, just because I have to, that those missions are in competition with another very cool mission that's trying to grab a piece of a comet and bring it back to Earth, and we'll see who wins. But let's now talk about Titan. So here's a picture of Titan. It's Saturn's largest moon. It's the only moon in the solar system with a substantial atmosphere. We knew Titan was very interesting because when it was first observed, actually going back as far as the early 1900s by a Spanish astronomer named Joseph Camasola, he claimed to see limb darkening and suggested it had an atmosphere. I questioned that measurement, but that was the first paper that said Titan had an atmosphere. It was discovered again in 1944 by Gerard Kuiper, who took spectra of Titan and said there's a substantial gaseous methane component, which only happens if there's an atmosphere. That was interesting enough that the Voyager mission was diverted. One of the Voyager spacecraft were diverted to see Titan. And because they went and imaged Titan, they then never got to go into Uranus, Neptune, and Pluto. And this is that Voyager photo of Titan showing a hazy orange atmosphere. The Pioneer spacecraft was actually the first to take a photo of Titan, but Voyager was the one that then characterized not only the picture of the atmosphere, but also the composition by shining radio science experiments. So it's putting Ka-band radio through the atmosphere and watching how it gets refracted before it gets back to Earth. You were able to tell how big Titan was, and also the fact that at the surface, you have an atmosphere that's 4 times denser than the air in this room, and at a temperature where that methane that we know is in the atmosphere acts as a liquid. And so we knew there was potentially a liquid component on Titan, and that that methane that makes its way in Titan in the upper atmosphere, what happens to that methane is the same thing that happens to methane that makes it to the upper atmosphere of Mars or Earth, and that's high energy particles from the sun will photolize it, knock off a hydrogen. Methane is carbon with 4 hydrogens. High energy particle from the sun, or sometimes Saturn's magnetosphere, will knock a hydrogen off. And so you have an organic chemical factory in the upper atmosphere of Titan that is creating complex organic molecules. If you take an Orgo textbook, close your eyes, open it, and just put your finger down, you're probably going to hit a molecule that might be being generated on Titan. And so when Titan, and then because of that, the methane and the highest quantity product of that photolysis, ethane, are both liquids at the surface, led people to conjecture that beneath this atmosphere, there could have been a liquid ocean that covered the entire moon. And that's where we sat. I just tried to speed through that a bit to say we're sitting at a position. Titan is an explorer's utopia. And what NASA's next flagship mission after Galileo was Cassini. Do people know Cassini? Heard of Cassini? Okay, great. And Cassini had a European contribution that was the Huygens probe that actually landed on the surface of Titan. So that means that Titan is the second moon, other than our own moon, to have a man-made object on its surface. But when they designed that probe, because we didn't know whether Titan's surface was liquid or solid, that probe was either made to float in a methane-ethane sea or land on a solid surface. And so that gives you a sense of the excitement. It's just always exciting because you don't know what you're going to find. That's been general for all planetary science, but especially true for Titan. And that's how I started out my career in planetary science as a graduate student, is coming in just as the Huygens probe was landing. And this is a snapshot of just the break room at where I went to grad school, Caltech. This is the break room at Caltech where professors and students are taking bets on what the Huygens probe is going to land in. It's just really exciting atmosphere. Some people said ice, some said tar. Darren Ragazine, he's a professor at BYU now, said it's going to be liquid. I'm going to get my John Hancock and say that. Undetermined, Mike Brown's the one who got it right. It's tar, but we can't tell. If you guys have ever worked with Mike, he's also the one that pioneered demoting Pluto from a planet to a dwarf planet. So I will never tell him he's the one that's right, but he did. Some pessimists said dead on arrival, and then Dave Stevenson, who those folks who work in geophysics may know the name, is a very great, really nice, very renowned professor. He's the kind of one you expect to see with, like, you know, the elbow pads on his jacket. And he said it was going to be eaten by a sea monster. And I still haven't gotten him to commit, but we named all the large seas of Titan are named after sea monsters. And so I think there might be a connection, but I've never gotten to be able to prove it yet. Either way, this is what Huygens did see. This is an artist's conception. This is the image from the surface of Titan. This is an image on the way down. What it found was an Earth-like landscape with an extremely different set of environmental conditions. And so on the way down, this is an 800-high mountain, and these black patterns are dendritic channels that are carving into a water ice hill slope. And the channels are made of liquid methane. Huygens landed in what looks like a floodplain with rounded cobbles 10 to 20 centimeters in size. No large-scale liquids here, but many familiar surface processes. And so that's kind of been the statement of Titan. Titan is a place of familiar physics, strange environments. We have the same processes modifying Titan surface that modify Earth's surface under very different environmental conditions such as gravity, temperature, and material properties. And it really is a natural laboratory for studying how surfaces evolve. And just to give you a quick tour, the equatorial of Titan, maybe from 20 south to 20 north, is dominated by these long linear features. Most of what you see here are radar images because that's the instrument Cassini brought to penetrate through that thick atmosphere. And you know, when we first started getting this data, this is very pre-pandemic, right? We're locked in 2005, 2006, but we still had an international team. And so whenever data came down, we get on telecons. And we do this remotely. It was by the phone, not the computer, but we do this remotely. And Ralph Lorenz, who's the project scientist of the next Titan mission I'll mention, called these things cat scratches because he didn't want to suggest that they were any kind of process yet because we had just gotten the data. And here's the fun anecdote. Rosalie Lopez, who's also on the team, stops at the Vons supermarket just outside JPL for her coffee every morning. And the day after we talked about cat scratches, she saw this in the Weekly World News right by while she was paying for her coffee. And she literally got all worried that somebody had broken into our telecon and that security was compromised. And so now instead of one passcode, I had to put in like 2 or 3 to get into future telecons. As it turns out, this was some reporter got this idea because he was at a bar with some of the Huygens engineers in Europe. And they were just joking about the Huygens probe finding mutated cats or something. I don't really know, but it was just kind of funny. In any case, what we're looking at instead, go back to it, are linear dunes. And these are linear dunes that are extremely similar in both size and morphology to the dunes you find in sub-Saharan Africa or in Namibia. In terms of size, they're about 100 to 200 meters high, kilometer spacing. They have 30-degree slopes, but instead of being made of silica sand, these guys are made of organic particles. So they're basically 200-meter high piles of plastic being blown around by the wind on Titan. And to this day, we still don't understand how you actually create those particles. Do you create a crust on the surface and erode it? Or do you scintillate things as they come through the atmosphere? I personally think you erode crusts, but we still have no idea. And that's one of the things we need to just get on the ground to see. But these dunes are pervasive around Titan. You just aeolian processes of the default environment where you have dry properties and wind. Okay, we can see the cats again. You also see fluvial processes or rivers on Titan. Not only do you see rivers, you see different kinds of rivers that tell you about different processes. You see gravel-bedded rivers, you see braided rivers, you see rivers that tell you that they're formed on steep slopes, shallow slopes. You see river meanders, which says there's something cohesive going on in the surface that we don't understand. And then in 2016, we looked at altimetry data, and Valerio Poggiali, a postdoc in my group, now a research associate in my group, found that some of the rivers that go in the North Polar region are actually these steep-sided 300-meter deep canyons with greater than 45-degree sloping walls. I don't know how you dig into these so steeply. We don't understand it. Is it mechanical erosion, dissolution? We still don't know. I will say, for those of you familiar with Ithaca, I am kind of embarrassed for this, but when we published this paper, we had to do a press release, and I couldn't help myself. The topic of the press release was Titan is gorgeous, which, if you've been to Ithaca, it's a very cliche statement, but we did it. In any case, there's a lot of questions surrounding these rivers, too. Rivers on Earth exist because topography is generated on Earth, mountain building, right? And then the rivers start eroding down the topography. If we have active rivers on Titan, why haven't they eroded away the topography? Is there topography being built up on Titan somehow that we don't understand? Or are these rivers frozen in time, where the sediment, where they're all bedrock at the base and they don't actually transport sediment? If they do transport sediment, what is that sediment? How do you generate that sediment in the first place? What are the hill slope processes that produce the sediment that then gets moved to these rivers? These are fundamental questions that we can't answer with the data we have, but will be hopefully answered by getting images down on the ground the first time we just see what a river looks like. Nevertheless, we'll try. An undergrad in my group, just to drive home some of those points, started mapping all the rivers on Titan, and then also mapped rivers on Earth at high resolution, and then degraded the resolution of those images on Earth to what the equivalent resolution is on Titan, mapped them again. And sadly, what we found was that all of the metrics we use to try to understand river dynamics, things like network classification, branching angle, were a function of resolution. She got different answers, whether she did it on the low-res data or the high-res data, which really brings us back to the question of we need to get back to Titan with higher resolution to resolve what's going on. Okay. That same postdoc who did the altimetry data then went back and looked at it and said, hey, you know, we could do a lot better in this altimetry. And this is where I mentioned I'd talk about some new data coming from Cassini. Certain instruments on Cassini, in particular the radar instrument, a lot of the processing to turn that into usable data happens on the ground. And when you have advancements in the algorithms that are used to generate radar images or altimetry, you actually can go back and reprocess the data. And so he went back and used some advanced radar processing that's done on Earth on the Titan data, and we were able to increase the resolution of that altimetry data by using Doppler bins by a factor of, say, 4 to up to 10 for the distant observations, and reprocess that data and look at it again and make new discoveries. And we're doing the same thing now with the SAR images, applying that same advanced processing, and we're about to, well, we're going to ask NASA for money to produce it, but assuming NASA pays us to do it through a proposal, we'll be able to reprocess all those images from Cassini with a factor of up to 2 to 4 increase in their resolution, and hopefully help us a little bit determine some other features. But I won't get into the details of how that works. The point is, radar is to some extent radar voodoo, and there's some really great stuff you can do if you want to enhance the processing if you haven't fully taken advantage of the Doppler resolution. So here's a picture of lakes and seas on Titan. This is Ligeia Mare. It's the best image lake we have. And I just want to sit on this for a couple seconds to point out that if I didn't tell you this is Titan, that this could be a large lake or small sea here on Earth. There's so many familiar features. This is a false color image in radar, but I'll just point out a few things. It's just fascinating to me. One would be Vid Flumina, which is this large scale river. The tributaries of Vid Flumina are where we discover those canyons. So the 300-meter deep sea-sided canyons cutting into the surface. Where does that sediment come from? And you can see here that the lake is encroaching up Vid Flamina's valley. So it's a flooded river valley similar to Sydney, Australia. That's an evidence of sea level rise. The lake's rising and drowning existing topography. You also see these crenulated terrains up here. These are like the fjords of Norway, where you had steeper topography that's being flooded out, and that's how you create those sharp boundaries. There's also places where you see flat, straight sections that could be evidence of beach processes and sediment transport and material being produced and being eroded and moved through by waves. And there's a lot of science and ideas that one has to go through to look at this and ask the question of, does this coastal landscape tell us something about the timescales associated with the processes modifying and eroding Titan? I don't have too much time to get into it, but all of the seas on Titan are seen in the North Pole. And when you look at the South Pole, you see evidence of dried up seas, paleobasins. And part of the idea is that on Titan, just like on Earth, there are these Milankovitch cycles where you have, right now, it turns out that summers in the north are colder than summers in the south, because when summer happens in the North Pole, you're about 1 AU further from the sun because of the orbit than when you're in the South Pole. So southern summers are hotter and shorter, but the nonlinear mechanisms that cause evaporation will actually transport more liquid from the south to the north. So you build up over time, you drain your liquid in the south at your north. But the position of the seasons on the orbit changes. This happens on Earth too. It's one of the two driving factors of ice ages. And so when the thing was switched, which happens on 30 and 100,000 year timescales, the idea is that the liquid then flips between the north and the south. And that's why it's consistent that the sea level is rising. But how quickly can you move that fluid? Does it happen? Those are all still outstanding questions. Another interesting observation looking at this lake or sea is that when you look at the ends of these large river valleys, you don't see deltas. You don't see sediments like the Jezero Delta that Mars 2020 is currently investigating. And we just have a paper coming out that shows that if they were there, we should see them. And so there aren't deltas here. Why are there not deltas here? Do they not have, are the rivers not bringing sediment? Do they not have enough time to create them as the sea level is going up and down? Or does it have something to do with the interesting dynamics going on here, which is another difference from Earth? So I mentioned on Titan that there's two liquids at play. There's methane and there's ethane. And so you actually have a ternary fluid where the atmosphere of Titan is made of nitrogen, and nitrogen dissolves in your fluid, and your fluids are a mixture of methane, ethane, and nitrogen. But there's very little ethane in the atmosphere at any given time. So when it rains methane. And these rivers are going to flow methane into the sea, which has more ethane in it. Now, why is that interesting? It's interesting because nitrogen likes methane. And you dissolve about 25%, a liquid of methane in equilibrium in Titan's atmosphere is about 75% methane, 25% nitrogen. But ethane does not like nitrogen. And so when your methane-rich fluid, which has a bunch of nitrogen in it, flows into your more ethane-rich sea, you exsolvate nitrogen. It's bubble city. And so as these fluids are flowing in here, there's probably the whole sea looks like it's boiling, which is kind of cool. What does that mean for sediment transport? I don't know. And we've tested this in the lab of just flowing methane into more ethane rich, and you do see these bubbles of nitrogen just popping up. But it's just an interesting question that has not quite gone to fruition yet because it requires a little bit more lab work of what does it mean when you have ternary fluids that are interacting with each other. Now, another thing that we had a campaign for looking at those lakes and seas is looking for waves, and talking about how you create waves on Titan is a whole other story I'm happy to get into afterwards. But during the search for waves on these lakes and seas, a pair of postdocs, Marco Mastrogiuseppe and Valerio Poggiali, working at Cornell, discovered that unlike liquid water on Earth, liquid methane and ethane is fantastically transparent to microwave energy. And so when you look at the altimetry data, which means you're looking at the lake and sea with the radar, and you shoot down, and we were looking to see if the sea was flat or rough, if there are waves on it. But when you plot time, or in this case, distance from spacecraft, time over the speed of light, against power, you see this bright peak, that's the surface of the sea, and you see the secondary peak. That's the bottom of the sea. So the radar wave is penetrating through the sea, going down through 200 meters of liquid in this case, reflecting off the bottom, coming back up and being measured by the spacecraft. So this was completely unexpected, and it's really fun because it's discovering another way to use the instrument that was not conceived when it was launched. So basically, we're using Cassini as a fish finder. And when this was discovered and verified, there was a proposal made to the Cassini project that said, hey, we know all your flybys are planned, but look, this radar can be used to do this new thing. Can we do it? And they rechanged the end of the mission to have flybys over all the major liquid bodies to take advantage of this new capability. What can you learn from this capability? One, by just looking at the distance between the two peaks, you get the depth of the sea. And by looking at the ratio of power, you know how much how much of the energy was absorbed by the liquid column, which you can invert to give you the complex dielectric constant, which through lab work can be directly related to composition. And so we get the depth of the sea, and assuming it's a mixture of methane, ethane, nitrogen, we get the composition of the sea. And what we found was, unlike expectations, the sea was not ethane dominated, it's still methane dominated. And so one of the fundamental questions post-Cassini on Titan is, where's all the ethane? Okay, so we did that on a whole bunch of seas, and what that allowed us to do is then build up bathymetry maps by combining it with SAR data and actually give a measure of the liquid. And so when you do that, what you find is that all the liquid hydrocarbon exposed on Titan is about 14 times the volume of Lake Michigan, or 300 times the mass of Earth's proven natural gas reserves, or 35 times the mass of all terrestrial fossil fuel reserves. And I'm sad to say that I used to parrot this slide around when I was trying to get a Titan mission selected to say, if NASA doesn't do it, I'm going to Exxon. But in any case, something that you can also learn from this is that if you take all the liquid hydrocarbon on Titan and spread it around the globe, you get about a meter of liquid. About a meter. If you take all the liquid hydrocarbon or all the methane that's in Titan's atmosphere and condensed it out, the precipitable column depth, which is what you call that, is 7 meters, which means there is 7 times more methane in Titan's atmosphere than there is on the surface. Let's do the same thing for Earth. On Earth, if we take all the water out of the atmosphere and spread it around the globe, it's about the thickness of your thumb. It's about 2 centimeters or an inch, whereas the average depth of the oceans is a kilometer. And so that's a completely different thermodynamic regime. On Earth, a lot of heat is transported in the oceans because that's where the sink is. That's why you have ocean currents being so important. On Titan, the lakes and seas are more tracers of what the climate's doing, because they just don't have either the connectivity or the volume of material to have all that energy. So it's just a different climate system. All right. So again, we did the campaign. We got this at all the different seas and lakes over a period of years, and we're just publishing the final papers in that campaign now, just talking about the difference in composition and bulk composition and depth. I will say there's a lot of error in doing this, but hey, you're using a radar around Saturn, looking at Titan to measure the composition and depth of the seas. We can accommodate some error. I do want to quickly mention the other kind of lake you have on Titan. You have these large seas. Everything else are these small lakes that come in both empty and filled forms. And these things are unique to Titan. They're a unique feature. We call them sharp edge depressants. These guys are strange. So what they are flat floored depressions about 300 meters deep. You can see it here. They grow by scarp retreat based on their shapes. It looks like they grow into each other. And what's really confounding is when you look at them with the altimeter, both the filled ones and the empty ones have 1 to 300 meter high raised rims around them. So they're steep-sided depressions with, there's the liquid surface, and there's rims on each side. You can see, because we're coming at an angle, there's 2 rims, the one here. And here again, raised rims. And there's a whole paper on this from 2018. Please read it. If you have any ideas on how to form this thing, please tell me. The end result of this paper was, here's all the things it can't be. Now help me out with what it can be. Because we still don't know how you actually form these materials. There's no inflow or outflow channels going into them. So dissolution is been thought of as the way you most likely generate them. When you're dissolving away the material, it means they can't be made of water ice, because you can't dissolve water ice with liquid methane, ethane. But the real confounding thing is, how do you form these raised rims? And then if they grow, how do you destroy and reform the rims as they grow? Very confounding feature, unique to Titan. But getting back to our story, what we're working on right now in my group is we just finished really analyzing the campaign of those bathymetry measurements. Marco is now in University of Rome La Sapienza doing it. Valerio still at Cornell. But what we've also collected during the Cassini mission are what's called bistatic experiments, where the Cassini orbiter sends a radio pulse at an oblique angle reflecting off of a lake or sea of Titan. And that energy then goes back to Earth and is measured by the deep space network. This is a common experiment that's done on planetary surfaces. What's cool about doing it on a liquid surface that's so smooth is that you get a factor of 1,000 higher signal than you would if it was a rough surface. And what's really nice is that you can do this near the Brewster angle, which is the angle where you get no penetration. And so we're really interrogating, instead of the whole liquid column, the very top surface of the liquid. And this is all fresh, hot off the presses analysis. It's actually quite complicated to take out all the effects of Earth's atmosphere, Titan's atmosphere, the moving spacecraft. But we send out one polarization of light, and we measure both that come back, because when you reflect off a surface, a component of your reflection will switch polarizations. And by looking at the ratio of the received polarizations, we can directly measure the dielectric constant, the real component of the dielectric constant. And we've done that through a series of these passes. And this is a word chart. I'll just tell you what we found. What we find from doing that is that when you look at the seas, first of all, the dielectric constants seem a little low, which might suggest there's some kind of film on the surface of the seas. But what we do see in general is that the deeper parts of the seas have higher dielectric constant, which means more methane, more ethane. And when you look at the estuaries, the places where the rivers go in, you actually see lower dielectric constants. And our interpretation there is that the rivers, which are methane rich, are flowing into the seas that are more ethane rich. And so it's the equivalent of brackish water on Earth, where you have freshwater rivers flowing into a salty water ocean. And so you have slightly more methane content right where the rivers are going in. And we see that in both Ligeia Mare Cervis Fritum, Boson Sinus, and Mare Sinus, in 3 different places where the rivers enter the big seas, where we have large river systems, lower dielectric constant. That's kind of cool. We also see that the largest sea crack in Mare has a little bit more ethane in it, or a little higher dielectric constant than Ligeia Mare. And that's consistent with a theory proposed by Ralph Lorenz, saying that because there's a gradient in precipitation with latitude and the watersheds, you actually flush more fresh methane through more northern seas, and so those are more methane rich, and the lower ones are more ethane. There's also pluvial processes, or rain, on Titan. This is a slide from 2011, a science paper by Zibby Turtle, the PI of the Dragonfly mission, showing a large-scale rain event that blacked out 500,000 square kilometers of an equatorial terrain on Titan. And you know what this told us is kind of what some of the GCMs predicted, in that when you look at Titan, when you look at Earth, you have 1 centimeter, as I said, of precipitable water, and then you have 2 meters of average evaporation minus precipitation over a year. And so what that means is that you dump out your column of 2 centimeters of water every few weeks, right? So rain events on average happen every few weeks in any given location, changed by the seasons. On Titan, the basic physics says something different. You have 7 meters of liquid in the atmosphere, but you only have tens of centimeters of energy for evaporation precipitation. And so the concept is you dump out an atmospheric column's worth of liquid in a torrential downpour, and then you wait 10 to 100 years for it to rain again at that same location. That's the basic idea. People are trying to model that now with GCMs. And that explains how you create these dendritic channel networks during torrential downpours that happen infrequently. And there's a campaign with one of my previous grad students now working at Millennium Spectral that does ModTran. And we continue to look at Titan with various observatories on Earth. And this is just the latest series of large-scale clouds we saw just this past fall. And there was also a recent cloud event observed by JWST that came out as a press release about a month ago. And we have this monitoring campaign that shows, without getting into detail, that basically the position where you see the large-scale cloud systems that could be convecting trends to higher latitudes with time with the seasons. When it's summer in the south, you see clouds there. When it's during equinox, you see clouds at the equator. When it's summer in the north, you see clouds there. There's also craters on Titan, but very, very few craters. And craters on Titan are unique and interesting in that when you hit a crater on the moon that's made of basaltic rock, you create a melt pool at the base of solidified lava. When you hit a ice crust like Titan, you create a melt pool of liquid water. And so depending on the size of your crater, Titan's thick atmosphere is very insulating, and the liquid water underneath maybe a small ice crust on the top can last for hundreds to thousands of years, interacting with the organics on Titan's surface. And so these, we call them Darwin's small little ponds, are natural astrobiology experiments, and actually the target of the Dragonfly mission going back to Titan, is to look for a melt pool in the center of a crater where you had liquid water interacting with Titan's organics for some period of time. I'm running low on time, so I'll just keep going. Some cryovolcanic processes on Titan. We're very smart out in the Cassini team. Randy Kirk, very smart guy, had this really great idea. I asked him, what's your favorite feature on Titan? He said it's Dumas Mons here. It's the best evidence for cryovolcanic processes because of boom plot. We don't know any other way to create a 2-kilometer hole in the ground next to a 1.5-kilometer mountain, but yet we also have no idea how you can have explosive volcanism happening on Titan. Either way, this is currently the best example of a potential cryovolcanic feature on Titan. We need higher resolution imagery to look for associated flow patterns and so forth to demonstrate this was some kind of cryovolcanic event. Nevertheless, Popular Mechanics rated this the best volcano in the solar system a few years ago. I don't know who they consulted with on the Cassini team too, because everyone I know was just as surprised when this came out. Like, what? But anyway, Dumas Mons is the best volcano in our solar system, including Earth. All right. So Titan is really at the intersection between terrestrial planets with an atmosphere and the ocean worlds of the outer solar system. As I mentioned, it's a world of 2 oceans. I didn't really get into the prebiotic chemistry here, and rightly so. There are much better experts in the room than me on this, but I also just need to mention, because of the importance of what Dragonfly will be doing, that Titan's methane-rich atmosphere, having that organic chemical engine I mentioned, is a reducing atmosphere that it's not exactly the same, but it is similar to the atmosphere of early Earth during the emergence of life. And one of the things we want to understand is what molecules are generated in that atmosphere and delivered to the surface. There's also the question of whether you can have totally alien biology. Isaac Asimov, Life as You Don't Know It. And this is a question of whether there could actually be life in methane and ethane seas on Titan. This is very challenging because, first of all, it's very cold, right? 93 Kelvin. And second, methane and ethane don't like to dissolve things like water does. So the concentrations of the things you have to work with are very low. Nevertheless, in my next slide, I'll show you that the Templeton Foundation paid a couple of Cornell professors for a few years in a collaboration to figure out whether or not you could come up theoretically with the mechanisms necessary for life in a Titan methane ethane sea. And the answer they came up with was, we don't know if it actually will work, but yeah, we can do things. Other things are, you could have hydrothermal systems at the base of the ocean, and then you also have those impact crater melt pools. So here is what you can do on Titan. You could use acrylonitrile. There's a paper in Science Advances in 2015 showing how you can create inverted cell walls. So you can create an inside and an outside. You can use acetylene to produce energy. And then hydrogen cyanide can be used to create precursors to RNA peptide chains. Actually, Miranda, Chris's grad student, is working on something similar to this for Earth. But I don't want to spend too much time discussing this. Happy to answer questions later. There's also the question of whether you can get that acetylene that's deposited on Titan's surface. Remember, Titan is different because of all the organics being generated, and deposit them into the liquid water ocean. And I'm part of probably the last active standing NASA Astrobiology Institute before they turned into research coordination networks that Rosalie Lopez is PI of to try and answer these questions. My group is associated with building landscape evolution models to talk about where you might transport material and how you might get it down. And then others are working on what kind of chemical reactions you could do if you get the acetylene in there, and whether you can have Heliobacter acetylene nicus, if I said it right, which is a bacterium on Earth that uses acetylene for energy. Is there a Titan equivalent? So we're going back to Titan. This is the output of the last New Frontiers program with the Dragonfly spacecraft. There's some involvement in Dragonfly here at Penn State. Dragonfly is a nuclear-powered rotorcraft that'll fly around the equatorial region of Titan to study its dune environments, measure the astrobiology of what the composition is of the surface, and ultimately make its way to Selk Crater to look for a melt pool inside the crater itself. And just being able to get there, touch things, see on the ground, will just revolutionize our understanding of Titan. It's going to be quite the exciting mission. It launches in 2027, lands in 2034. Happy to answer any other questions about it. It'll be looking at the prebiotic chemistry of creating the atmosphere, measuring the atmospheric conditions, methane reservoirs, and then it will search for biosignatures as much as they are present on the surface. So really, with closing, I'm going to mention not just Titan now, but going back to Europa and Enceladus as well, and Mars, is that I honestly believe that we stand on the verge of a golden age of exploration for the solar system, looking for signs of life in the ocean worlds of the outer solar system or previous signs of life on Mars. And it just means a lot to me to say that within certainly your careers, for those of you that are in the class, and maybe my career, we might actually get an answer from one of these missions that are targeting the search for life. And